Yeah, there we go. That's a little bit better, right? Seems that the fourth lecture today and tomorrow is a little bit kind of out of line with the previous lectures, and so you're up for a bit of an entertainment, but also very useful message. So relax, enjoy. I'm going to motivate this talk by saying that NFXP that Bertel was talking about requires full solution of a model. This talk is about only solution of the model. I will say a couple of words which you can do later with this. And of course, I mean, the intention is to plug it into the estimator that would require solving the model completely and then maybe simulating from it or maybe calculating some sort of other statistical criterion. That's one thing. Another thing is that, as Bob taught us, there is no difference between micro and macro. This is really used a lot in macro, but I don't see any reason why this cannot be used by micro people. And another thing, if you haven't seen the endogenous grid point methods before, it's like magic. You'll love it. Okay. So with this, let's begin. We will focus on discrete and continuous choice. The thing is that endogenous grid point methods were originally developed for the just continuous choice consumption savings, like the standard macro model. But we wanted to do more with data, and it turned out to be really interesting mathematical kind of challenge. So of course, the discrete and continuous choices are everywhere, and we usually either abstract from one side of this choice problem or discretize everything altogether to put it into one domain. But yeah, the problem is that with discrete choice, we can optimize our finite set, which may take more time. With continuous choice, that would be first order conditions. But as I will talk or show you in this lecture, there's a lot of interesting features that appear there. Okay. What are the problems with these models? Or again, features. In discrete continuous choice, if you combine this in a dynamic model, you get intrinsic non-concavity of the optimal optimization problem. So already on the capital T-1, you get into the situation where the optimization problem may have multiple local maxima. First order conditions are not going to be sufficient, therefore. And in the dynamic context, these problems will manifest themselves as kinks in the value functions and even discontinuities in the policy functions. So like I said, this is pretty exciting. If we try to just approach this problem with the standard toolbox of dynamic programming, then what you have to deal with is the need for global optimizer in each point in the state space. And I will show that in a bit more detail, or maybe mention once more. You need to do something with these kinks and discontinuities. So non-differentiability and of various sorts. Maybe you need to come up with special numerical procedures to be efficient about dealing with these problems. Now, the endogenous grid point methods started as a quick and very accurate method for solving consumption savings problem. Turns out to be really useful in these settings as well, and you will see that. So plan for the lecture is to cover three things, well, four actually. I want to talk about the original EGM, endogenous grid point method, with one continuous choice only, to bring everybody to the same page, how it actually works, and then introduce discrete choices. Now, when we introduce discrete choices into this problem, then things become nasty and scary, with all these discontinuities, accumulation of kinks, and all sorts of problems. And then we go to the kind of the standard theory of discrete choice. The idea was that can it help us in the numerical sense? And if you add taste shocks, which can actually be interpreted in both ways, the way that Bob was talking about in the beginning, right, as something not observed that is important for the choice. But you can also think of this as just purely numerical smoother. You can try to smooth your nasty functions by adding a little bit of logit error. Things suddenly become much more tractable. And you know, this has been going on for what, about 10 years now. There's more and more work every year coming about, and I will talk about the extensions. The thing which is really hard is multidimensional setting with the same approach, and hopefully I can give you some idea of how that can be done. Okay. So what is EGM? The method of endogenous grid points. This is a fast and very accurate method for solving a particular dynamic programming problem or a particular class of problems. It can do finite and infinite horizon, that's no problem, but it has to have strictly concave, monotone, and differentiable utility function to be really good. One continuous state variable, one continuous choice variable, and a particular structure on the law of motions of these variables. And yet, you know, constraints are kind of hard, but some particular constraints turned out to be really easy. So the borrowing constraint is really easy to deal with. Now, the DCEGM, the discrete choice version of the EGM method, will keep kind of the general setting. So the strict concavity of the differentiability of the utility function, will be still there. We will have this continuous state variable, which is singled out with a particular motion rule. We will add additional discrete variables, which can have transition probabilities that have to satisfy certain additional criteria. So the transition probabilities, oh my God, I'm pressing the wrong button all the time. The transition probabilities must be independent of that specific state variable. And then we'll have one continuous and one discrete choice. Now, one discrete choice variable, of course, is the same as having as many discrete choice variables as you want. You can just re-index them. So that's not a constraint of any sort. Like I said, we will look at two flavors of this DCEGM algorithm without the taste shocks, and then the one which is smoother and kind of easier to operate with. What are the learning points? If the model has one continuous and one additional discrete choice, DCEGM is probably the best way to approach this model that there is. In regular cases, DCEGM avoids all root finding procedures. And of course, that means that this is super fast. If the utility is separable in continuous and discrete choices, then the credit constraint is not a problem, can be accounted for in a very efficient way. And as I said, then you can use this with the numerical or logit smoothing to get a much better behaved setting. Okay, so I don't know whether you're working with a problem that fits this description. If you don't, then the point to take, maybe I should add another one, is like algorithms matter. Okay, you really want to study your problem, and like Bertel was saying that, you know, switching to Newton-Kantorovich from successive approximations at approximately right time is the difference between being able to solve and estimate the model and not being able to solve and estimate the model. So this is also a message about, you know, there are these algorithms which are just amazing, and we need to know about them. Maybe you can adopt it to your setting. All right, let's start with EGM. Consider this really, you know, Econ 101, 201. Oh, question. Going back. I will point to the papers which laid out explicitly. Yeah. Thanks. Okay, let's look at the consumption savings problem. We have a single state variable. This is going to be cash in hand, or all resources available for consumption in period t. I'm writing subscript t's as if it was it was finite horizon, but we can actually think of these as iterations in time as we solve it. So it actually can cover both finite and infinite horizons. We're maximizing up to this level of wealth that we have in period t, so there's no boring. The Bellman equation contains, of course, the utility of instantaneous payoff of consumption, plus the continuation value, and the intertemporal budget constraints will be very simple here, right? So R is the deterministic or stochastic return on savings. I'll look at deterministic setup first, and this is everything that's left after consumption, right? We will have a special letter for this asset left after consumption, and we will call it the end of period asset. Okay, this is nothing but the difference between MT and CT. And imagine that the utility function is CRA, you know, a log for starters. Now, this is a really nice problem, right? This is Phelps consumption savings problem, which has an analytical solution. Here's the analytical solution. You can find in the literature. You can actually derive it yourself if you want to do some manual by hand backwards induction. Okay, that means that we can really test whatever method we have for solving this model against the very clear, very specific, very accurate analytical solution. What are we looking for? We are calculating this value functions in different time periods. If it is an finite horizon problem, then you know all these correspond to the different time periods, and you will be able to show me the solution of the infinite horizon problem, right? Where's the solution of the infinite horizons? Anyone? Speak up. Flat line, so the bottom line. Well, I mean, as we do the successive approximations, the value functions converge, right? And then we stop doing successive approximations when, you know, the ones that Bertel was talking about, when the Bellman operator has a fixed point, and, you know, as you converge, you probably should expect that the value functions kind of get closer together. So I think the infinite horizon solution is this on the top here. And then, you know, looking at the policy functions, these are the functions, these are the fractions of the available for consumption wealth that you should optimally consume in each time period. And by the same logic, the infinite horizon solution is on the bottom here. Okay? Well, if we modify the problem just a little bit by adding this additional income term here, then the problem doesn't have the analytical solution anymore. Right? We need to do something numerical. What would we do? How would we solve this? If I just do backwards induction, you know, value function iteration in infinite horizon, or just backwards induction in the finite horizon. Well, the first step is to think about a grid on this continuous state space. We are going to be programming this on a computer. We need to discretize. Okay, so let's fix grid on MT. Then we go into our usual backwards induction procedure. For capital T, we're maximizing the utility function without having this continuation value. Nothing happens in the last moment. Or you can think of starting with 0 value function when you do the infinite horizon problem, right? So the next iteration will not have any value function. Same thing. There's going to be an argmax, and that describes the policy, the optimal policy in capital T. Now, with the assumptions that I made on the function monotonically increasing concave, this solution here is just to consume everything, right? You want to get as much as possible of this utility, so the C star T is just equals to MT. And then as we do the backwards induction, then we're solving this equation and calculating the optimal choice. Well, now what is it to solve this equation? In each point MT, we're solving an optimal or maximization problem, which takes time. Whether you do it through first order conditions or just the maximization, you have to iterate over the CTs and so forth. I was going to run some code, and there's code in the repository for MATLAB and Python. And I'm just gonna ask. So there's some code here, and if you look at the folder corresponding to MATLAB, that's the file that you will see. Okay, I have these little switches here, so we will set up the problem and then solve it with VFI here. Okay, let's try to run that. The file name is run DSE. And what you're looking at is the solution of different points in the state space of a 25-period problem, right? And it didn't take too long, just drew some dots to entertain us, and produced the set of the policy functions which tell our agent how much to save or how much to consume. Okay. Let me go back to the lecture, to the slides. That's all I wanted to do. Alternatively, we could write down the early equation, right? And let me skip the derivation. The early equation that describes the optimal choices in two adjacent periods. It's just basically a combination of first order conditions and the envelope theorem. Tells you that you have to equate the marginal utility of current consumption to the discounted expected marginal utility of future consumption with the growth factor there. And we could, in principle, also solve early equations to calculate this optimal choices. Again, fix the grid over M. In the terminal periods, solve the that problem, which is kind of very simple, and otherwise solve the equation that describes the optimal choice. And then again, iterate it until convergence, or iterate it back until the first period. So what are the problems? Well, root finding is slow. That's not the only problem. If, as I said, we will go to a non-convex optimization, then it would be hard to find global optimum because of the existence of local solutions in each point of the state space, potentially. So in each point of the state space, we're solving a hard optimization problem. Now, another thing is that we will see is that because of this fixed grid up front, we will not have any way of finding some special points which turn out to be important. Because there is no way to kind of beforehand, a priori, to put a grid point where you want that. Now, without numerical optimization, that would be much, much better, right? Much faster and potentially more accurate, as it turns out to be. So EGM, brought to economics by Chris Carroll in 2006. Very short and nice paper. I didn't see how many citations, but we must have a lot of citations at this point. The promise is that what if we didn't have to do this root finding operations? And the idea is very simple. Instead of searching for the optimal decision in a fixed point in the state space, we can actually find the point in the state space where a particular decision would be optimal. And so it's kind of turning the problem inside out, right? We can go through potential decisions, outcomes, and then recover the points in the state space where this potential outcomes would be optimal. And therefore, the grid becomes endogenous. Let me just jump into the algorithm and let's see how it works. So first of all, this is backwards induction. We will be doing the standard iterations from capital T, or from the first iteration of the infinite horizon problem. And there, let's just say that there's no bequest motives. It's optimal to consume everything. And here's the EGM step. On each time iteration, we will do many of these EGM steps. But one EGM step starts with choosing an A that we will think of the current period savings, so end of period wealth. Okay? Once we have A, then we can calculate the next period wealth, because that would just grow with some interest and give you the point in the next period wealth. Because this is a backwards induction, we already know the policy function in the next period. So we will be able to calculate the optimal consumption in the next period in T+1. Okay, and then we have early equation. The early equation will put into correspondence the optimal choice tomorrow with the optimal choice today. And if you have a luxury of inverting the marginal utility, then this is analytical. And so what we get is the point which is the optimal consumption in period T. And we started with some savings level in period T. And so then the last step is to just put them together. And that gives you the M, right, the points in the state space for which the corresponding CT and that A that we started with are optimal consumption and savings. And now we just do this step many times for all different values of A. And that essentially recovers a table of the endogenous points in the endogenous wealth, the corresponding optimal consumption and the corresponding optimal saving. And we can use that as to calculate the policy function on the next time, on the next iteration as we go to yet t-1. Okay, makes sense? So a good way to think about this is this. Given the early equation, we are interested in this function C of M, which would describe the optimal behavior, which is the policy function. Well, just writing this inverted early equation here, and then the expression for the state for wealth for the state variable, which is the C plus A, right? So I can just write the inverted early equation again. What we have is essentially a parameterized curve. So you have a parameter A, and that just traces out this function that you're interested in, the function C of M. And now you can basically look at the grid, fix a grid over A. Oh, I don't know, adaptively come up with points A using some additional algorithm maybe. And recover these pairs of endogenous values of state together with the optimal consumption. Okay, are there any questions to this? This is what we call EGM step. It's really fast and it's really easy to code up. Here's again, this is a MATLAB implementation. There's the Python implementation as well. Oh, I started to talk. Max, can I please ask you to put a link to your package into chat so that everybody has the link? There's now a wonderful implementation in Python of this whole EGM and DCEGM methods. But yeah, if you think that it's hard, no, it's not. 11 lines. And it's also really fast, right? The speed comes from the fact that we don't need to iterate on to find any optimal actions. This is just direct calculation. In addition, it's really precise. So if I look at the maximum absolute error in the levels of the and the mean of this computed optimal policy, it's better than the traditional time iterations with Euler equation. Why is that? Well, because we are using Euler equation to recover this points. Yes.
Same size that you grid for C and the grid for A, it's the same size.
You're asking about these results here? Yeah. I believe that I've solved the with EGM and then had a denser grid to calculate Euler errors. Okay, yeah, just to give you an idea how fast it is, it's pretty fascinating. Let me just run a couple of examples here. So you remember how long it took, just to see, it's working okay. It's not immediate, and of course you have to wait for quite some time if you're doing nested estimator, where this has to be done for every value of a parameter. And now let's just switch to EGM here, and let me just run it again, and we're done. And by the way, we've done not just once, we've done 100 times. So that was, let me do it again. No, pay attention. That's it. So this is 100 times that we've solved the model. And then, of course, simulating consumption paths, once you have this collection of policy functions, is a simple task. And let me just do the following exercise here. You can see that we're changing parameters of the model in such a way that the discount factor exactly equals to 1 over 1 plus R. This is deterministic interest. And this is the case where the early equation predicts completely flat consumption paths, right? You get marginal utility of consumption on both sides and leading to the optimal consumption to be equal in the consecutive periods. So if I just run this, oh yeah, okay, first value function iterations, sorry. And then we can compare. So these are two simulations of consumption, which are started at some, two values, and then the calculated policy function, calculated by the value function iteration, is applied every period, the normal way that you do the simulation. And you can see that the error is really small in the beginning. I mean, they should be flat. They're just a little bit not flat in the beginning. But because of the error accumulation, towards the end of life, you really have to compensate. And so slowly but surely, this optimal decision gets out of whack, and then you have to compensate. This is probably overcompensation. Then the lost consumption gets really small. So if I do the same thing for EGM, I just change the solver here. That's what you get. Right, so this what theory predicts, and that's what you get with EGM on the same sizes of grids. And there's an anecdote when I was working with Michael Keane on this method, and well, not exactly this, but with discrete choices, it's harder, right? Then we had many times this interaction when I would come and say, it's almost flat. It's almost flat. And he would say, no, go look for the bug in the code. It's not flat yet. Let me switch back to the slides. Okay, just a couple of words about the credit constraints. Turns out that if you have a monotone and concave utility function, then end of period asset is non-decreasing in M. Okay, why is that useful? Well, that's because when we have the freedom of choosing the asset, this end of period, asset, the savings, end of period asset. We have the freedom of choosing it. And so we can run the EGM step for A equals 0, right? And that would recover the point where this constraint just becomes binding. This would be the point where the constraint is binding, but the early equation still holds. The early equation holds due to the EGM machinery. But due to this result, it means that for all of the values of the asset less than this calculated level, the constraint must be binding because of the monotonicity of the end of period wealth. And that means numerically is that we essentially run this loop of the EGM loop for different values of A. And if I start with A0, that would give me a point here, and then some other points. This is the optimal savings function as a function of wealth. And then to take into account the credit constraints, all you have to do is to recognize that below 5, below this level where early equation holds, but the constraint is binding, the constraint will be binding. So you have to save nothing. You have to consume the 45-degree line. And so now you have this complete policy function with credit constraints. Sometimes, we will see that we will have to calculate the value function as well, just in a moment. And if in this region where the optimal savings is 0, actually the value function has this form, where the EV t+1 of 0 is just the expected value of starting the period with 0, essentially, right? Like saving nothing and starting the period with 0. Of course, it only makes sense if there is income, because otherwise consumption would be forced to be 0, and that's where the problem blows up. But this value is going to be fixed if the utility is not time dependent, right? So this is essentially constant. This is essentially constant, and in that sense, we have value being defined as an analytical function on this credit constraint region. This is going to be helpful. Okay, any questions to EGM? It's magic, isn't it? just solves the problem really fast, very accurately. Let's make it work with discrete choices. Must be a good idea. Yeah.
You said that this only works in mostly best works when the state variables is univariate. Was that it?
Well, it's written for univariate state variables. You can allow for additional state variables, but the catch here, and we will probably see it, yeah. The catch is that everything about the future can depend only on this end of period savings. So, okay, let me go back to this description. So over here, there's going to be an expectation. We don't know the MT yet at the time when we have to compute this expectation. So if the problem allows all of the transitions conditional on the state to be equivalent as conditional on the A, then you can do it. Right, so A, in that sense, A has to be a sufficient statistic, right, for M, in some sense. Everything in the future can depend on A, but not on M. And it holds in many applications. It's not really important whether you condition on the beginning of the period wealth or end of period wealth, not crucially important in a dynamic model. Okay, let's now turn to DCEGM. Right, so the idea is kind of appeared pretty soon, right? Julia Fella had a paper published in 2014 where he looked at the just generally on non-smooth and non-concave problems in dynamics. And we had a similar idea, but we were motivated by discrete continuous choice combination. They're slightly different, and you know, it turns out that adding adding the taste shocks in particular in this extreme value distribution sense actually helps a lot. So let me restate the problem. This is now consumption savings with an additional state. Additional state basically says whether this agent is a worker or a retiree. Okay? If the agent is a worker, then and continues to be the worker, then there is, I'm sorry, yeah, then there is this income in terms of, say, wage income. This is conditional on continuing to be a worker. And if the agent retires, then we are back to the consumption savings setting that we had in the very beginning. Now, just for the purpose of the presentation, I'm going to assume that if the agent is already retired, then there is no additional discrete choice. So retirement here is absorbing. It's very important to say, and I get this question quite a lot, is that this is not crucial. This is just to have one Bellman equation to talk about. In principle, you could have this 2 lines on the second option as well. Now, what are the 2 lines? This is essentially just the choice between retiring or continuing to work. So this max is over 2 options, and then in the same time, you're choosing the optimal consumption in that time period. How does it reflect in preferences? Well, if you're a worker, then there is a cost to pay to be a worker, the disutility of work. And again, let's start with deterministic problems. So Y is going to be deterministic wage income, and R tilde is going to be just R. Right, this problem turns out to be also possible to solve almost analytically. And the solution is given by this combination of segments, should I say, that prescribe optimal consumption levels at different levels of wealth. You consume everything if you're below Y divided by beta, deterministic problem, right? And then you consume, this is a linear function of wealth every time in these different brackets. The solution looks like this. So if we are in capital T minus 2, then there's a region in this green line where it's optimal to consume everything. Then when it deviates, optimal consumption deviates from the 45-degree line, that's where it becomes optimal to save a little bit. But then suddenly there's this discontinuous drop to a different segment of the policy where, you know, for some interval here, it becomes optimal to save less than before. And then again, and as you can see, as you go back from the capital time period, then the number of these discontinuities grows. Okay, and now DCEGM is the method that is going to be very accurate in reproducing this pretty crazy optimal savings pattern or policy function. It's not really a pattern. So here it's very important to keep in mind the distinction between the optimal policy and the simulated consumption path. Because this just prescribes the optimal levels of consumption for different cash in hand. How the path will look, we don't know yet, right? It does not have to be discontinuous at all. So let me try to construct EGM now in this new world. So the goal is going to be to avoid root finding. I think that's the killer feature of EGM that we would like to keep. It would be nice to also keep efficient treatment of the credit constraint if possible. Now, the main idea is to say that, let's just condition on a discrete choice and do the normal EGM at every state. I have allowed for this additional state, Dennis, in this formulation. We can compute the D-specific value function and the consumption rule. So this is where it becomes important to also compute the value function corresponding to this discrete choice on which we conditioned. And then we can compare these value functions, right? These are the value functions that Bob called conditional and Bertel called choice specific. These are the value function corresponding to these different options in discrete choice set. If we compare them, we can calculate, in which regions of the state space of wealth it's going to be better to be on one regime or the other regime. And, pretty straightforward upper envelope exercise. We just want the maximum of this multiple value choice-specific value functions. But then to each of these choice-specific value functions, there will be its own consumption rule associated with it. And so then we have to also combine these different segments of the policy function and put them together into a single policy function. And that kind of tells you where these discontinuities are actually coming from. Okay, no root finding, right? We're not solving equations anywhere. Efficient treatment, we'll get to that. Needs to compute value functions. So there's going to be more work to be done, although this is not a very big additional work. But then we also need to compute the upper envelope. That's a little bit more tricky. Okay, one thing that needs to be cleared up is that will Early equation even hold in this new setting? And this paper, which I think is published now, so I should add the journal, gives the answer. Given our assumptions on the utility function, it turns out that when we intersect value functions, the kinks that appear are kind of downward pointing. They establish that it will never be the case that the optimal consumption will, or the optimal solution of the maximization problem will actually be in the non-differentiable point. And that basically means that, yes, we can use the Early equation. Okay, so let's go. Capital T, we have two value functions corresponding to two different discrete options. Remember, this is where it's optimal to consume everything. But if you work, then you pay this penalty for work. And there's no future. And so this working value function, this is a choice-specific value function. And I'm only now going to be looking at the worker who has the choice, right? We said that retiree for now is an absorbing state, so we don't need to look at that. We already solved it. Now, for the worker, there are two choice-specific value functions. It's obvious that you want to retire in the last time period. Now, if you go to capital T minus 1, the picture changes. So the blue line, it was the retirement, right? This is the solution of the normal consumption savings problem. And if I run the EGM step for the worker, I didn't draw that analytical part of the utility function, of the value function here, but this is what EGM produces. This last point corresponds to saving nothing, to saving 0, and there are many points that kind of form this green line. You can clearly see the intersection. So why do we have an intersection? Working is good because there's going to be income next time period. But retiring is good because you don't have to pay this utility of work. And so there will be a trade-off that kind of makes this intersection point appear at some level of wealth. We have wealth on the horizontal line. Okay, that's the idea, right? So we have two intersecting value functions. We're searching for maximum value, kind of going back to solving the normal Bellman equation that we started with. And so the value function of this capital T minus 1 period is going to be given by this red dotted line or dashed line as an upper envelope. And you can see it gets a kink. The kink in the value function here is because you would be in different regimes. You would be either retired if you're retired on that side, if you have enough money, or working in capital T minus 1 if your wealth is lower. Now, in anticipation, what Euler equation will do at that point, the derivative of the value function changes discontinuously here. And so the Euler equation will jump essentially if you look at if you put everything on one side. There's going to be discontinuity here just because of this kink. All right, but before going there, let's just put together the two optimal consumption functions corresponding to these two different regimes. And please disregard these vertical lines. They're not there. This is actually a discontinuous consumption function. So when you're a worker, you are consuming a little bit more than if you were on the right side of that kink, a retiree, but not very wealthy. Yeah.
Why did you have a value function like a dashed line below the level of saving 0?
Because there is a value of having even less money. You are on the credit constraint, you're consuming everything, and this is that analytical part. That's where it's equal to the utility function plus a constant. Huh? Yeah. So below, to the left of this point, you're consuming everything. Essentially, that's just the part that corresponds to the credit constraint. Okay, so this is the capital T minus 1 optimal consumption function. Fine. So what happened? We had these specific value functions intersect. We calculated the upper envelope. There was a kink. And you can see also that this kink was kind of pointing downwards. That's what the Clausen and Straub paper is talking about. The upper envelope has a kink, and the combined consumption function has a discontinuity. Did we expect that? I don't know. Are we surprised? Like, are you convinced that there's a discontinuity? Any questions about that? Okay, let's continue. Now going to capital T minus 2, doing exactly the same thing. Conditioning on working, conditioning on retirement. The retirement function looks fine. And if you look at the working, there's this very strange bow tie region, zigzag region. So we were working on this with Bertel, and when we saw this, we were really puzzled. What's going on? Is it like instead of a value function, you get a set valued function somehow? What was going on there? If you zoom in, what happens is this thing. Actually, it was kind of zigzagging between some points. We used at that time pretty dense grids because we wanted to get more accuracy. And somewhere in the code, there was a sort of the endogenous grid points for whatever reason. So it turns out that there were all these endogenous grid points, many of them in this region. And once we sorted the endogenous grid, then there was a zigzag produced. But what is actually going on? Well, what happens is that because the value function has a kink, the derivative has a discontinuity. And that kind of translates to the early equation to the existence of the region in wealth, this region or this region, from this wealth to this wealth, when the first order condition is just not sufficient. And so as you follow through all possible savings, this earlier inversion, the EGM step, recovers not only the global maximum, but also the other maximum, the local maximum, which is not global. And how do we know that? Well, to that point, that point satisfies the first order condition just by construction, by this EGM construction. But if you look at the value, you can clearly see that it's suboptimal. It's below this red line. And so what would you do with, I mean, after realizing that just having a kink, having the non-convex problem, you could get things like that. After realizing where this, additional points are coming from, then you can see what to do. And what do you do? Well, again, you just need the upper envelope, right? You're maximizing the value. This is the value, and this is your state. You're solving the Bellman equation, the maximization and Bellman equation. So the solution is really just to calculate this additional upper envelope. And what about this point? See, this point also is a kink, essentially. Yeah, this is an illustration of that of the early residuals. As you go through the relevant values of state of wealth, then this discontinuous earlier equation, for some levels of wealth, has multiple solutions. And EGM basically traces both of the solutions because they correspond to different levels of savings. If you don't sort, okay, then this is the behavior that you will see. Imagine that you've sorted your end of period wealth and you're going from 0 up, 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 right? Then you will be producing points like this. And then at some moment, the next produced point will be here. And then it will nicely go upwards again. This is wealth, and this is optimal. No, this is value function. Okay, so this is the representation of that bow tie zigzag region in the actual kind of order that the points are produced by the EGM step. And again, here it's very obvious what to do, right? We just need to calculate the upper envelope, and we have to say or recognize that these points here, they are just suboptimal. They are the points where the first order condition holds, but they do not correspond to the maximum of the value. And then this additional point here can be placed as a kink point where these two branches have an intersection. And we are using linear interpolation everywhere. Maybe there's so this is going to be placed with some accuracy, with some error rather. Maybe there are other ways to do it more accurately. Okay, so how do we algorithmically detect these regions? I mean, you want to write a code that just solves the problem, right? You don't want to observe and kind of treat these regions in a special way. So again, we're using the same monotonicity result under weaker conditions. Essentially, like I was explaining, if we sort the exogenous, or as I was given in the example, if the exogenous grid over the end of period wealth is in ascending order, then every time the produced endogenous point kind of goes back, jumps back, that's an indication of the failed monotonicity, and therefore you can kind of split these two branches of the value function over here and calculate the upper envelope. That's the idea, yeah.
If we place into the utility, so you have a pop diagonals with consumption and L, labor supply, and then we interpret the labor supply as the common solution. So if we have 0, that's not working. If we have 1, that is working. If it's in between something.
So this is almost the same.
Will that model modification solve the kink problem?
That's a very good question. And so here's the answer. First of all, you will be able to run this EGM in a nice, efficient way if you can invert the marginal utility of consumption. So that's one thing to check. The second observation is that this problem really appears if the labor supply decision has some dynamic implications. So in here, we assume that if you decide to be a worker today, then the income comes tomorrow. So there is this disconnect between the decision and the reward. If you have in the model anything like human capital accumulation or some various dynamic implications of the discrete decision today, then you will have this problem, these kinks. If the model allows for the labor supply decision to be treated as a static decision, then you can essentially solve for it somehow and write down the indirect utility function and get rid of this additional choice at all, completely. You don't have to do it, but in principle, that's possible, and that's how you're getting out of the problem. So it depends on the model design in the end of the day. Any other questions? Nope. Okay, so here's how the algorithm works. Now we've put numbers on this generated points generated by EGM. I have another half an hour, right? Yeah, 35 minutes. And so every time you have this jump back, then you separate the value function correspondence into two sectors, two segments, and calculate, and you kind of start the upper envelope calculation on these two segments. They will intersect, and the upper envelope calculation can calculate the actual, cleaned value function. When you do this, then you will see that point number 8, 9, 10, 11, 12, 13, 14 are suboptimal. And they correspond to some levels of consumption, okay? But we are going to just drop them. These points will be irrelevant as suboptimal. And so that's how you get this consumption function to drop at this kink, additional kink, and get another discontinuity. Okay, so let me skip that and talk about this. The big picture, if we have discrete choice, the choice between retirement and work, there is going to be something that we call refinement threshold. The primary kink over here, the kink that comes about because there is a switch between discrete options. But then as we go back in time, in the deterministic setting, there will be kind of echoes of those kinks in the future, which we call secondary kinks. And they are just because the problem is non-convex. They are around just because the early equation may have multiple solutions for some levels of wealth. The optimal consumption now in capital T minus 2 looks like this. Again, disregard the vertical lines. This square here denotes the primary kink. If the agent has more wealth than, corresponding to this, more than 12, then it's optimal to retire. If the wealth is less than this, then it's optimal to be working. That's the kink that separates the two options. Now, this is just a point, This is just the point from which this agent acting optimally will find themselves exactly at the kink in the next time period. So this is that point where you have to already adjust the consumption, whether you're on either side, because of the kink in the next time period. Another question.
No reason to ensure that the secondary kink is just one, or
one?
could be just more than one.
That's what we get. Here's the answer. So as you move back in time, then every secondary kink, by the same logic, will have a mirror in the previous time iteration, and primary kink as well. And so what you end up is this really discontinuous policy functions, similar to the ones that I showed in the analytical solution in the very beginning. Now, you can also look at the optimal retirement policy, and this is now has wealth on the vertical line, and this is time. And so like we were saying in the last period, this is a 25-period model. It's optimal to retire no matter what wealth, but then it takes some wealth, and the wealth level increases as we go back to retire optimally if you are richer than that particular threshold. Okay? So this is a discrete policy function in some sense. Okay, so once we've explored all of these details, what is the algorithm now? Well, we can start from the terminal period, compute optimal consumption rule value function, and then loop backwards, EGM step for each discrete choice, one by one, compute the specific value functions and consumption rules. That's what we wanted to do. Now, there are secondary kinks. So secondary kinks have to be cleaned out. So there's this additional step, compute secondary upper envelope over the zigzag regions for each of the D-specific value functions that we're computing. And then update the corresponding consumption rules. And then we can compare the D-specific value functions to find that point where the primary kink is. And then again, reconstruct the consumption level around the primary kink, and then go into the next iteration. Okay, so that's how algorithm looks after trying to go through with the EGM step through this DC problem. Now, it's very important to highlight here is that algorithm became kind of complicated. Well, this is not because of the solution method. Right? Every problem that has this discrete and continuous choices combined with this, like we've discussed, dynamic implications of the discrete choices will have value functions which are non-concave, will have discontinuities in consumption rules, and kinks will propagate through time. So that makes this deterministic version of the consumption savings problem with discrete choices or any other sort of non-convexities really hard. But DCEGM works well. If you have a dense enough grid, then we can basically replicate that analytical solution. Let me demonstrate. So think about this. In this problem with retirement, if I set beta r equals 1, so if I force a flat consumption profile, should we expect it to survive the retirement moment or not? So here's what the code looks like. I'm setting up the model for retirement, 500 grid points. This is the condition, right? And no, we taste talks. Then we solve. And then plot various things. Let me run this. Now it takes a little longer to solve DCEGM, right? Because of all these secondary kinks. But that's the answer. Right? So this is a simulation of a consumption path, starting with two different values. When you start with, it's a little bit of a cheating, I guess, because when you start with 1 point, then the scale of y-axis will adjust and make it not look so nice. But in general, we get a really flat consumption profiles in the simulation, even though people retire at different times here on these dashed lines. Okay, and so this, what does it tell you? It tells you that even though the policy function is crazy, discontinuous, all these different segments, you initialize a person with a particular wealth, and then even though the policy function looks really complicated, then it reflects the behavior where they consume exactly the amount, such that they will jump around from one segment to the other and always keep the same level of consumption, even through, before and after their retirement decision. So in some sense, this model is kind of hyper-rational. I mean, the optimal rule is really complicated. And our agents here who we model are able to compute this perfectly, such that even in that really complicated environment, they can enjoy their consumption being completely flat. Okay. What happens with random returns or any sort of stochasticity in the model? Well, random shocks help. That's kind of the big message. But then how much of them you have to have is unclear. Let me just run a few pictures through. So this is a random return. So we are calculating expectation around all these kinks. And the standard error in the, I think it's log normal returns with the standard error of the underlying normal distribution being 0.1. You can see that the primary kink is still here. This is an optimal consumption function for capital T minus 3, wealth and the consumption, right? And then this kink is smooth. This is one of the secondary kinks which gets really nicely looking. Why is that? Well, remember the logic was that the secondary kink is exactly the point where the agent knows that they will be at the primary kink tomorrow. But now they have no way of knowing, because now the the return is going to be random. Is it income or primary kink? Okay. Yeah, I think it's random returns. There's no way of knowing that you will be exactly at that primary kink tomorrow. And therefore, this shadow kind of gets blurred, this shadow. But look, here, this is still vertical, and so this is still a discontinuity. And what is that about? Well, when this kink is blurred, the value function still is non-convex around this smooth point here. And that means that even though it's, it's not a kink on the value function, it's smoothed, but it's still is not smooth enough to make it convex. And you still have a discontinuity the year before, because there are still multiple local optima, and the early equation is not sufficient for finding the optimal level of consumption. But if you, I'm looking at a little bit more. If you go back in time even more, then all this starts to be smooth, and this is smooth, but these are discontinuous. We can try to add more randomness into the model. So I'm now increasing the sigma, and at some point, this one is also smooth. But it's no way of knowing when that happens. And yeah, the corresponding picture for the value function shows you that, this 2 steps ago, this was a kink, even though it's really hard to see that it is, but the derivative changes discontinuously. And over here, it's already smoothed. Okay, let's jump into the new idea. So how do we smooth primary kinks? Can we just try to get rid of the kinks altogether? Well, no amount of stochasticity in the model will change the fact that at some point it will be optimal to retire or stay working. So this primary kink is impossible to get rid of by just adding more randomness to the model itself. And therefore, we need to do something special. And so what's that special? Extreme value, the new normal. Bob didn't want to talk about extreme value too early. And I mean, we don't have to, but this is so convenient. That's the new normal. So we reformulate the problem. Now I'm rewriting the same problem of retirement in the choice-specific value function space. Now this small v's, they now have 2 arguments. This is a worker. The second argument is a state who chooses to continue working or who chooses to retire. Okay? The Bellman equation is going to look like this. Now it has this additional random parameter scaled with sigma over there. And the choice-specific functions look as before. The expectation with extreme value assumption will be given by the log sum, the log of the sum of the exps. We have this scale, right? Scale is going to be interesting because we can change the amount of randomness that we add to these discrete choices. And then the actual value function, the value function for the retiree is basically, or the whole Bellman equation is not changed, right? So again, not to talk specifically about the retiree, we just keep them as being already solved, kind of. Okay, so what happens if we add this extreme value shocks? You can, I'm waving my hands now. You can think of the early equation to be discontinuous for the reason that tomorrow, the optimal level of consumption depended on whether you were a worker or the retiree, and therefore the marginal utility changed discontinuously. It turns out that if you derive the early equation in this problem with extreme value shocks, then what you get is this. Oh, sorry, my fingers are too large for this clicker. What you get is this. So now you're equating the marginal utility of consumption today to the discounted expected weighted sum of the marginal utility of consumptions in 2 different regimes, retiree or worker, and the weights are actually choice probabilities of tomorrow. And so it smooths this kind of discontinuous early equation, adding the extreme value shocks, or adding any sort of shocks, except for the extreme value, we have this nice analytical representation of the choice probability. And so if we look at that picture of the early residual that we had before, with like discontinuous change of this no taste shocks case, and 2 solutions, actually we made our life a little bit worse. Now early equation is continuous, but may have 3 solutions, okay? May. Now the whole answer now is that how do kinks accumulate? We saw that that a little bit of randomness in the model kind of smoothed the problem as you went backwards, and definitely killed this perfect accumulation of kinks where the number of them was larger and larger in the along the solution. What happens here if we don't even have the primary kink, which kind of gets everything going? Again, the DCEGM algorithm also becomes a little bit simpler. We don't need to do these steps at all. We're just solving the problem now in a different space. We're solving in the choice-specific, this conditional value function space. And instead of calculating the primary kinks and computing the upper envelope, we can calculate choice probabilities, right? By plugging this choice-specific values into our probability formula. So that's what happened, essentially. Now, it's easier to compute expectations because of the numerical methods just work better with continuous or smooth objects. But of course, more memory is required because of the need to store choice-specific values. Now, we can think, like I mentioned in the beginning, we can think of this additional noise, the logistic noise added to the problem as just a logit smoother. So we could say that, okay, we are dealing with these discontinuous objects. Numerically, it's much more convenient to have them smooth, and kind of a standard approach is to add a little bit of a smooth max or a logistic smoothing to the discontinuities. And this basically tells you that by choosing sigma, this scale of the extreme value shock, you can limit or bound from above the difference between the smooth and the non-smooth version of the problem by this, essentially. So it's very often includes it's proportional to the log of the number of choice options. Now, if you don't want this additional noise in the problem, right? You can just basically limit it to be, I don't know, $100 per year or something. And still, numerical methods would be much better working. Okay, if we look at the policy function implied by this smooth problem, then they are getting smoothed along with the increase of the scale. Of course, in the limit, when this sigma is very large, nobody is caring about the values. People are just taking random choices, like in the normal discrete choice theory. And so we can vary the scale of the shocks. Important thing here to notice is that there are still sharp declines or even discontinuities that can be present. And therefore, looking at the algorithm, this step where we calculate the secondary envelope and kind of get rid of the suboptimal points is still very important. They can appear. Okay, just a couple of words about the credit constraints. The approach is the same to calculate this level of wealth, to the left of which everything is kind of easy, right? Credit constraint binds and the value function has an analytical solution. But now if we, let me just click through this. If we do it for each discrete choice independently, then what's important is the minimum of these levels of wealth. And to the left, for the wealth below this point M, we have all of the value functions to have analytical solutions, including the choice-specific value functions, of course. And under additional assumption of additive separability, so imagine that the utility of wealth or consumption is additively separable from the utility of discrete choice. That makes this whole thing to be constant to the left of this common threshold. And that means that the value functions are parallel in that region, and choice probabilities just do not change. And again, you're getting to this situation where for very extremely low values of wealth, you don't really need to compute anything. It's all analytical or even constant, right? And that's where the problems usually appear in numerical solutions. That's where wealth is really close to zero. Okay, so to illustrate that, what I was saying is that, there's this point here and here corresponding to the zero savings in two different regimes. And we have analytical forms of the value functions. And with additive separability, essentially the choice probabilities calculated from these two levels will be constant on the corresponding interval. Okay, I think in the interest of time, I'm going to skip that and talk a little bit about generalization. Questions so far? No? No. Now, all of this is really good, right? But the class of models where it applies is kind of small. And so a lot of people are thinking about how we can generalize on endogenous methods. This is a recent survey written by Fella, downloadable from his website, which kind of lists everything that happened in the last, well, in all of the years. The development happened in the last 5 to 7 years, maybe. Let me just give you a quick overview. So the first paper which thought about how to do this in multiple dimensions, and by multiple dimensions I mean multiple continuous choices, okay, was Barillas and Fernando Villaverde, and their idea was, okay, we have two choices, let's just apply EGM to one of them and do the usual thing with the other. The usual thing was VFI, value function iteration. And it kind of worked, but you had to have a problem where you didn't have to iterate on one of the choices too much, because the overhead is kind of converting the problem from one algorithm to the other. Ludwig and Sean, this paper took a long time to publish, but they immediately saw the main issue with multidimensional EGM. The main issue is really interpolation. So if you have endogenous grid point, then you will have a two-dimensional grid which looks kind of like this, right? And here, if you have to compute something in a particular point, it's not trivial at all how to do it. You have to kind of look for the points which are close to that point of interest of yours, and do all sorts of the classical approach is what is called Delaunay interpolation, Delaunay triangulation, actually. And they show in this paper that it takes time. The Delaunay triangulation is essentially taking all of these irregular points in more than one-dimensional space and builds little triangles such that any point can be approximated by the nearest vertices of the triangle that it falls into. This is just computationally more intensive. Although I think there's a lot of people working on these problems because this is all about graphics. So this triangulation representation of surfaces in computer games, that's what this is really used for. So maybe we can borrow algorithms from computer science. But economists being economists, kind of developed their own algorithms, and Matt White, for example, has this approach where he's doing the visibility walk, actually also a known technique, where you have to kind of recognize that this nonlinear quadrilaterals, they are connected, and you can kind of follow a path to the points of interest, probably from the point of interest towards the axis. Alan Lujan recently worked and improved that method, also kind of part of the paper focusing on how to be efficient in interpolating on the irregular grids. You have to admit that, I mean, the idea here is that the grids are not too irregular, okay? They're not irregular like representing a surface of a mountain, you know, with very big changes of the altitude. They are kind of, you know, in the intermediate. They are irregular by definition, but they can be converted into something regular. So like Matt here, he basically takes this nonlinear quadrilateral and maps it one-to-one to a unit square, and then interpolates on the unit square and then maps it back with the inverse transformation. And similar thing happens here. Now, the paper by Jeppe Drudal, Thomas Jørgensen makes a big contribution in the in trying to solve you know, general multidimensional problems, including the non-convex problems. And they're talking about they're talking on this occasionally binding constraints. They're considering a problem with potentially many constraints that can come in terms of a discrete choice, or something else that constrains the choice of among the continuous variables. They have to do something with this multidimensional interpolation, and so their approach is to essentially re-interpolate on some regular grid of the state space, which allows to efficiently compare different segments or corresponding to different constraints, because the upper envelope has to be computed in any case, right, in multiple dimensions as well. I just wanted to show their policy functions. I mean, don't they look crazy? So it's possible to compute this. Now they're discontinuous in 2 dimensions. This is a problem with durables and bank accounts, I think, two continuous state variables. So this is possible. It's harder and it takes longer, but it's still possible to do. Now, a big theoretical question is, what is the actual class of models where we can apply these ideas? And I don't think we have a very clear answer. There has been a few attempts. So Matthew White had written kind of a list of assumptions that a problem has to satisfy. And his key condition is this invertibility conditions for the system of nonlinear equations. Something similar is in the Drew-Dahl and Jorgensen paper. They talk about injection between a particular map having this property. And then I had a go at this. And what I was trying to say is like to list the assumptions that would allow multiple dimensions and no root finding. So the previous papers didn't really focus on avoiding root finding. And I thought, okay, what's the biggest, most complicated multidimensional problem that can still be solved without the root finding? So I have about 10 minutes, is that right? Let me just preview what happens here. So imagine that we have this very similar structure, right, to a simple consumption savings model. But now imagine that M is actually a vector of 3. This is an example in R3. Is a vector, and C is a vector, and A is a vector. The idea is this. There can be settings in which there are multiple stocks of some asset. Can be money, health, I don't know, human capital. You think of stocks, but they could be controlled by different decisions, sort of like consumption savings. And then we would have to have this end of period or post-decision states in order to do the trick with the EGM loop. Okay, the evolution of this variables, let that be given by J, by function G. And then this is intertemporal evolution, right? So this is a mapping from my state space variables and choice state variables into this post-decision states. And then there's going to be an intertemporal evolution rule, which is like an intertemporal budget constraint, right? Which gives the state point tomorrow dependent on this end of period or post-decision states and maybe some shocks. Yeah, I'm abstracting for now from constraints. Let's just keep it simple. Okay, so first thing to notice is this assumption, right? And this will be crucial all the time with EGM or with any actually approach that is based on the post-decision states. You have to assume that the future only depends on this post-decision states and does not depend on today's M's or today's C's. And that's what we have in the consumption savings, because the end of period savings is exactly that sufficient statistic. Okay, so that's already assumed. And that means that in the Bellman equation, this expectation conditional on M and C can be actually rewritten to be conditional on A. We will have to, if we can do this EGM step in 3 dimensions, we will have to solve this system for all 3 variables. So let's make first assumption. This is just necessary, right? So I'm not trying to write anything sufficient. Let's just assume that this has triangular structure. I'm pressing the wrong button again. Let's just assume that this has triangular structure so that we can solve this equation to recover M, from this first line and then plug it in. This is, assuming that EGM will give us the optimal levels of C's, like in the consumption savings problem. Then we would be able to recover the optimal grid points M1, M2, and M3. Okay, and now let's just try to derive the earlier equation in this case, and I should probably skip that. The earlier equation is then represented by a system of equations. since there's going to be each choice will have its own first order condition, and there will be some dependence between these. Now, the structure of this dependence is actually already assumed to be sufficient for this to be solvable on the right-hand side. But now the crucial thing is that we can solve for the optimal choices of this whole system. So it turns out that the crucial condition is that the Hessian of the utility function is upper triangular. And so if you have this upper triangularity, then you can backward substitute, solve the equations one by one, and it should go through. Additional things are the usual condition on the utility, so that we can invert the marginal utilities. And then these functions are better to be invertible in M, the intratemporal budgets, so that we can recover the points in the state space once this the early system is solved. Okay, so it seems that these are conditions which are, I'm sorry, they are sufficient, right? I've misspoke. They are sufficient for the problem to admit this multidimensional EGM approach. Alan Luan has a paper recently about thinking of a decision process as kind of a sequence of different choices. So you can think of this as being kind of sub-periods within a period where different things are decided, and then applying the EGM ideas to this. You can look at this problem and conclude that this basically is saying that this triangular structure 1 is satisfied. So when the choices fall into this nice sequence, that basically says that this is a diagonal rather than triangular system. So you know, this is, you know, there are models, there are problems where this applies, and then of course the whole EGM can go through, and it would make things fast and nice. Now, sometimes you want to use EGM not because this is fast, and then you're not really interested in this analytical inverse of the marginal utility function. You can still apply EGM. If there is no analytical inverse of the marginal utility function, that means that there is still an equation to solve, right? So it kind of doesn't give you the main advantage. But it could be still very useful to be able to trace all of the points which solve the first order condition. So if you think what's the alternative would be to run some sort of an optimizer on the problem which is non-convex, and maybe do multi-starts to recover both of the local optima. Or you can run EGM step and completely recover with guarantee all of the points which satisfy the first order condition. And so this is the motivation for this paper. And then you can do things like, you know, if you have to invert the function which is not analytically invertible, well, maybe you can pre-compute and then interpolate the inverse and do a kind of numerical inversion, and still, you know, lose a little bit of accuracy, but still be able to trace all of the points that satisfy first order condition. Now, Wending Liu is my PhD student, and we kind of set up a model where there's no discrete choice, but there's a safety net, like a consumption floor, right? So again, very standard problem, but over here, you have a max over the resources tomorrow and some fixed level M0. And interestingly, it basically behaves as if that was a discrete choice. It's almost like a discrete choice of whether you land on this safety floor or consumption floor, or you actually do the savings. And so that kind of started here, but grew into potentially a new method, which tries to answer the question, you know, can we improve accuracy even more? So where do we lose accuracy with the DCEGM? The main loss is actually in locating secondary kinks, right? Because we're using value functions which are interpolated, and we are kind of linearly interpolate and approximately put the secondary kink in. And that is, you know, that has some errors. Moreover, think of the secondary kinks that happen really early before the primary kinks. So I don't know, 10 periods before. The area where the value function will kind of bend back is going to be really small, and it's easy to just miss it by not having a dense enough grid in that area. So DCEGM is a really good approach, but it's not perfect, right? What do you need to do to make it perfect? Well, let me skip all of this, similar things. But this paper recognizes the fact that you can build kind of a tree of segments of the policy function, which will be discontinuous through time. And then if you are willing to spend time to locate these points accurately by solving equations, then you can increase accuracy. And here's this new method, which, you know, this number of winners, that's, you know, by just running a simulation and comparing the utility, lifetime utility that you get from different solutions. And so Wending here, Wending and I will show that depending on the choice of the grid on the end of period wealth, on the post-decision state, you may actually lose accuracy with DCEGM, as you know, it's not a surprise. This works really well with in the deterministic setting, but it turns out that you know, there's literature which says that averaging over the deterministic solution may make sense. Okay. I'm out of time, but I have what, 3 slides left. What do you do? So where are we? I told you about this fast and accurate method to solve particular problems. It may be that your problem fits into this. It may be that your problem has a feature that this might be useful for. But I didn't say anything about data or estimation, right? So this basically says that if you know how to quickly solve a problem, then you can do a lot of things. You can build, you can calibrate your model. It could be, or it's a good start. You can structurally estimate by forming a nested estimator. But you could also do some other outer loops. Equilibrium would be an example, right? Or maybe individual heterogeneity. If you can solve this problem really fast, maybe you can solve this problem for every observation, every individual in your data, and be non-parametric about heterogeneity. Again, this paper in the reading list on the repo in the that you have has all sorts of applications. And I think it has an exhaustive list of everything that's been done with EGM in applications. EGM versus MPAC, no surprises. If you actually do an estimation, and so this was done in the time when MPAC was kind of very popular by Jorgensen, Thomas Jorgensen, you can see that the EGM is much faster and also delivers more accurate estimates. Well, yeah, or comparable or more accurate. If this is a Monte Carlo study of actual structural estimation based on EGM. All right. EGM, DCEGM, fast and accurate. No root finding. That's the reason. Deterministic discrete continuous problems are hard all the time, no matter how you approach them, but interesting. Kinks in the value function, discontinuous policy function, snowball effects in the accumulation of kinks and discontinuities. Extreme value or shocks with other continuous distributions will help. Extreme value will give you closed form solutions and can be added as a structural unobserved state, or can be treated as a smoother, just a numerical technique. And you know, doing this facilitates estimation using discrete choice data in presence of consumption savings. So useful in many different areas as we started. Let me stop here and give it to Dennis to explain what happens today next.